What if we could create our own black holes? Imagine that for a moment. Not the terrifying star-swallowing monsters, but something entirely different. Something small, manageable, and created by us. What if we could hold the power of a singularity right here on Earth? This isn't just a question for science fiction, it's a profound thought that pushes at the very edges of our understanding of physics. It asks us to look at the fundamental forces of nature not as things to be observed from afar, but as tools we might one day learn to wield. The implications are staggering, reaching into every aspect of our lives and our future as a species. This single audacious question opens a door to a future that seems almost magical. So, what exactly is a black hole? In the simplest terms, it is a place where gravity has become unimaginably strong. It's what happens when you squeeze an enormous amount of matter into an incredibly tiny space. Think of our sun. It's massive, over 1 million times the size of Earth. Now imagine crushing that entire star down until it was only a few kilometers across. The result would be a black hole. Its gravitational pull would be so immense that nothing, not even light, could escape its grasp. This is why they are called black. They do not reflect or emit any light, making them invisible against the backdrop of space. At the heart of a black hole lies a point called the singularity. This is a point of infinite density where the known laws of physics simply break down. Why would we ever want to create something so extreme? The answer lies in one of the most famous equations in all of science. E equals mc squared. Albert Einstein taught us that mass and energy are two sides of the same coin. This is the principle behind nuclear power, where a tiny amount of mass is converted into a huge amount of energy. But even our most advanced nuclear reactors are incredibly inefficient. They convert less than 1% of the mass of their fuel into energy. A black hole, however, is the most efficient engine of conversion in the entire universe. It could, in theory, convert mass into energy with 100% efficiency. Imagine a power source that could take any form of matter, our household waste, rocks, asteroids, and transform it completely into pure energy. The energy crisis would be over, forever. We would no longer need to scar the planet by mining for fossil fuels or worry about the long-lived waste from nuclear fission. We'd have a clean, compact, and unbelievably powerful source of energy. So, how could we possibly create one of these extraordinary objects? We can't crush a mountain, so we have to think differently. The most plausible method, though still far beyond our current capabilities, involves using incredibly powerful lasers or particle accelerators. The idea is to focus an immense amount of energy into a single, infinitesimally small point in space. If you can concentrate enough energy into a small enough volume, the energy itself, according to Einstein's theories, will have an equivalent mass. If that equivalent mass is squeezed past its own critical threshold, its own Schwarzschild radius, it could collapse space-time and form a tiny, fleeting black hole. Imagine a device that dwarfs even the Large Hadron Collider at CERN. It might be a sphere, many kilometers in diameter, lined with thousands of the most powerful gamma-ray lasers ever conceived. On command, all these lasers would fire a pulse of unimaginable intensity, perfectly focused on a single point at the very center of the sphere. Once we have created a micro-black hole, how do we get energy out of it? You can't just plug a cable into a singularity. The answer comes from one of the most brilliant scientific minds of our time, Stephen Hawking. In the 1970s, he stunned the world by showing that black holes are not completely black after all. He combined the theories of relativity and quantum mechanics and discovered that black holes should glow, very faintly. They leak radiation over time, a phenomenon now known as Hawking radiation. This happens because of quantum effects right at the edge of the event horizon, where pairs of virtual particles are constantly popping into and out of existence. Normally, these particle-antiparticle pairs annihilate each other almost instantly. But if a pair appears right at the event horizon, it's possible for one particle to fall into the black hole while the other escapes. For a tiny, microscopic black hole, the process is extraordinarily fast and violent. The smaller the black hole, the hotter it glows and the faster it evaporates. This is the key to our power plant. A microscopic black hole, with the mass of a large asteroid, would radiate with incredible intensity. It would glow with the power of millions of nuclear bombs, releasing its energy in a torrent of gamma rays and other high-energy particles. The promise of such power comes hand in hand with dangers of an almost unimaginable scale. We are, after all, talking about creating and manipulating one of the most destructive forces in the universe. The single greatest fear is a containment failure. What would happen if we lost control of our microscopic black hole? If it were to touch normal matter, it would begin to consume it. Even a tiny black hole, if it were to fall to the center of the Earth, could theoretically begin to devour the planet from the inside out. It would be a slow but unstoppable process, a doomsday scenario that would end all life as we know it. Therefore, the safety systems for such a power plant would have to be flawless and multi-layered. The black hole would likely be contained not by physical walls, but by powerful magnetic and gravitational fields, holding it in a perfect vacuum at the center of its chamber. These containment systems would need their own independent and redundant power sources, capable of running for centuries without intervention. How does this almost mythical power source compare to what we use today? Let's look at fossil fuels like coal and oil. They have powered our industrial revolution, but they come at a terrible cost. They release greenhouse gases that are warming our planet, and their supply is finite. Nuclear fission, which powers our current nuclear plants, is much more powerful and cleaner in terms of air pollution, but it creates highly radioactive waste that remains dangerous for thousands of years. Renewable energy sources like solar and wind are a wonderful step in the right direction. They are clean, drawing their power from the natural cycles of our world. They do not produce harmful emissions or dangerous waste. However, they have their own limitations. They are intermittent. The sun doesn't always shine and the wind doesn't always blow. To power our entire world with them would require vast areas of land for solar panels and wind farms, and colossal batteries to store energy for when they are not producing. Now consider the black hole power plant. Its fuel source is, essentially, anything. It could turn our landfill sites into fuel depots. It would produce no chemical pollutants and no greenhouse gases. The only byproduct is pure energy. Unlike solar or wind, it would provide a constant, reliable baseload power, 24 hours a day, 365 days a year. A single plant could replace dozens of conventional power stations, dramatically reducing our industrial footprint on the planet's surface. To master the creation and control of a black hole would be to change what it means to be human. It would mark our transition from a species bound to a single planet to a truly stellar civilization. The abundance of energy would solve many of the problems that lead to conflict and inequality today. Scarcity of resources, water, and food. With energy being almost free, the cost of everything else would plummet. It could usher in an age of unprecedented peace and prosperity, a post-scarcity economy where human effort is freed from basic survival and can be directed towards creativity, exploration, and discovery. This technological leap would propel us out into the solar system and beyond. Black hole-powered engines would make trips to Mars, the asteroid belt, and the moons of Jupiter and Saturn routine. We could build permanent settlements and industries throughout our cosmic neighborhood, drawing on the vast resources of space. This would not only secure the long-term survival of our species by making us multiplanetary, but it would also open up a new frontier for the human spirit. For all of our history, we have been explorers, and the stars have been our ultimate, unattainable destination. This technology could finally give us the key to unlock that door. Of course, the path to such a future is fraught with peril. The challenges, scientific, engineering, and ethical, are perhaps the greatest we have ever faced. It will require generations of scientists and engineers working on problems we can barely even formulate today. It will demand a level of global cooperation and wisdom that we have not yet demonstrated. The risks are existential, but the potential rewards are equally so. It forces us to confront our own nature. Are we wise enough to wield such power? Can we be trusted with the fire of the gods? The journey itself will force us to mature as a species. Ultimately, the question of whether we could power our future with black holes is about more than just technology. It is about aspiration. It is about our unyielding drive to understand the universe and our place within it. It is about looking up at the night sky, filled with its countless stars and mysteries, and not just seeing points of light, but seeing a destination. The quest for this knowledge, whether we ultimately succeed or not, will push the boundaries of science and elevate us. It reminds us that we are part of this grand cosmic story, and that our potential to shape our own destiny might just be as limitless as the universe itself.